Professor, my name is Minxin Li. Today my topic is new DC power grids for large-scale clean energy transmission. Here's my contents. First is background. Second is concept development stage. Third is engineering development stage. Fourth is post-development stage. Fifth is challenges, and last is summary and lesson learned. Firstly is background. As for clean energy, dispersion, small-sized, far from load centers are inherent characteristics. Traditional transmission mode, AC transmission systems for instance, is actually uneconomical. The way with more flexible, more economical, and more environmental transmission mode is needed. The development of high voltage DC HVDC transmission technology is closely related to innovations of converters. In 1990, DC transmission based on VSC converter was firstly proposed. Nowadays, many researchers have studied lots of aspects of VSC HVDC transmission system, but researchers limited in a single field cannot get breakthrough improvement. Next is concept development stage. First is needs analysis. That's Europe. The Europe holds the supergrid plan. Supergrid in Europe is the largest DC grid of the whole world. And next is Britain. The three-phase offshore wind power plant was proposed in Britain. HVDC transmission technology will be the theme of the third phase in the plan. In the meanwhile, grid interconnection between Britain and other European countries is on the table. Next is Germany. Double circuit transmission of AC and DC power among existing transmission lines is on the table in Germany. Next is US. Its Grid 2030 is a plan aiming to reinvent the US grid for 50% distributed renewable energy. According to this plan, coordination of power supply and demand among North America can be achieved by grid interconnection with high-capacity HVDC transmission lines and also long-distance HVDC transmission lines in regional grid makes it easier to optimize power resources. Next is developing countries. For India and Brazil, long distance between power sources and load centers. So VSC HVDC transmission systems will be established as well. And next is VSC HVDC. It has many functions. It can collect offshore wind farms with main grid to provide dynamic reactive power support and improve low voltage ride through operation ability of wind farms. Next, it can deliver electricity towards load centers of the city, and many advantages including black start, resolve voltage flinker, underground cables can avoid EMI, area of converter stations much smaller. And the third is grid interconnection. From AC, it can optimize power flow, and for DC, there's no commutation failure. And next is concept exploration. The early development of VSC HVDC transmission system. There are HVDC Lite from ABB and HVDC Plus invented by Siemens, but the topology of 2-to-3 level circuit leads to high switching frequency and power loss. Here's the hybrid HVDC. using LCC converter and VSC converter simultaneously. There's no commutation failure at LCC converter, and transmission capacity can be improved at a VSC converter as well, but actually it's not mature enough. Third is cost. As for cost, unit cost of VSC converter station will be 1.5 times that of traditional DC transmission system in general, but in the future, the cost will decrease gradually. I don't think it's a big problem. Next is empty DC. Since VSHVDC transmission systems can reverse the direction power flow flexibly, multi-terminal systems MTDC are more suitable. Recently, the topology of MMC MTDC has become the forward technical choice. The modular multi-level converter is cascaded by sub-module, and by approaching sine wave from step wave, the switching frequency of IGBT decreased from more than 1000 Hz to only 100 to 300 Hz. Next is concept definition. For MMC MTDC, there are many advantages. Low loss, good output waveform, expansibility, decreased harmonic wave, more flexible than two-terminal HVDC, and it can avoid static and dynamic voltage balancing problem by direct series of IGBT, and it can decrease switching loss and increase system efficiency. And here's the engineering development stage. After defining the model of MMC HVDC transmission system on the whole, there still exist some uncertainties in many aspects. First is advanced development. Research and development of networking devices plays a significant role in the future grid. First is MMC converter. The converter is the core equipment of DC power grid. As for MMC modular design, the modularity in structure makes it easy for converters to be assembled, and in this way, with the independence among sub-modules, requirements of higher voltage and larger power capacity can be satisfied by simply increasing the number of sub-modules. And there are plenty of advantages, including its low switching frequency, small harmonic disturbance, and easy to realizing high voltage multi-level output. Next is HVDC cables. Compared with overhead transmission systems, the probability of power failure is much lower in HVDC transmission systems, but HVDC cables need to meet the requirement of IGBT capacity and insulation, and also high voltage resistance must be satisfied. Next is engineering design. In addition to networking devices, power transformers and protectors provide a solid support for DC power grid. In this part, reliability, maintainability, and producibility will be taken into account. First is DC transformer. Not only should DC-DC transformers resolve fault isolation and ensure two-way flow of energy, but current harmonics need to be weakened as well. In fact, we use transformers in MMC HVDC transmission systems, and its main functions include the following aspects: convert the voltage of AC systems to the secondary voltage matching with the DC side of the converter, and it can provide a portion of commutating reactance. It can isolate the zero sequence component generated by AC system asymmetry. And the next is startup resistor. The starting circuit is the unique circuit in VIC HVDC transmission system. Before normal operation, MMC converters need to be charged in order to reduce the disturbance and voltage stress of diodes, which come from the charging current. We choose to connect a charging circuit in series between the MMC converter and transformer. And the third is protectors. First is high voltage circuit breaker. Actually, the high voltage DC circuit breaker with dual functions, control and protection, has become a bottleneck, restricting the development of VIC HVDC transmission systems. Overall, the hybrid high voltage circuit breaker is proposed with high current carrying and isolation capacity and breaking capacity. This new type circuit breaker is gradually becoming the first choice of VIC HVDC transmission project. Next, it's SFCL, superconducting fault current limiter. Using fault current limiting technology, SFCLs are invented. Low impedance is maintained in SFCLs while the system is healthy, and thus additional loss is low enough, and while a short circuit fault occurs, SFCLs will convert to high impedance quickly to limit short circuit current, and at the same time overcurrent is avoided. Next is DC smoothing reactor. It's actually designed for lightning protection and reduction of harmonic current. Here is integration and evaluation. First is differences with traditional AC transmission system. There are many differences, including major installation, device status, power flow control, and so forth. And next is engineering evaluation. MMC converters hold the ability of dynamic independent and fast regulation of active and reactive power flow distribution. That is, reactive power compensation devices does not need to be equipped in MMC converter stations. Thus, MMC HVDC transmission projects would cover a much smaller area than that of traditional AC transmission projects. Next is post-development stage. First is production. VIC HVDC, especially MMC HVDC transmission mode, will be in the midstream of large-scale clean energy grid collection. At post-developed stage, networking devices, including converters and cables, are successfully designed. As for the transformer and protector, limited by current science and technology level, further research is needed. Next, I will elaborate on the control mode and protection strategies. First is operation and support. First is control system. The structure of control system can be divided into 4 levels. Firstly, system level control (SSC). It is the highest level of the control system. It can take SCADA commands and realize the communication among control system and converter stations. It can generate power commands and operation mode commands, and then issue to converter level controller. Secondly is converter level controller, also named PCP. And third is valve level controller, VBC. And fourth is submodular level control, it's SMC. And third is main functions of control system. First, sequential control function. Sequential control, mainly including charging, unlocking, locking, third and reparalleling function, is to complete the automatic control of a series of operation steps through the control system. Next is power or voltage control, active power integrated control, and reactive power integrated control, and VF integrated control, DC voltage control, control mode selection or switching, 5 kinds of power control. And next is redundancy control. When faults are found, each control system switches redundant systems in time so as to ensure that the whole system is always in working state. Here is protection system. First, protection based on time domain information and protection based on frequency domain information. Protection based on time domain information is use the sampling value for calculation, in which the overcurrent, low voltage, and other protection principles can quickly detect the occurrence of the fault, but it is actually difficult to consider the selectivity at the same time. That is, the setting value is difficult to set. Second is converter station protection and DC transmission line protection. The converter protection is the core of converter station protection. The converter protection can be divided into over current protection, over voltage protection, valve short circuit protection, and etc. Actually, how to make full use of the control function to limit and eliminate faults is the difficulty of the future research. And next is loss analysis. It includes MMC, HVDC, converter station loss, and line transmitting loss. First is converter station loss. Includes MMC converter loss, transformer loss, reactor loss, and other equipment loss. Second is line transmitting loss. DC transmission lines include cables and overhead lines. A loss of cables is mainly caused by resistance. The losses of overhead lines mainly include corona losses related to voltage and resistance losses related to current. Next is measured results. Let me take an actual project case as an example. For Lan'an 3-terminal MMC HVDC transmission project in central China, the converter station loss accounts for the largest proportion of the overall transmission loss. It's about 70%. Next is power flow control, UPFC. First, transmission capacity analysis. According to the current scale of wind power, the maximum power transmission capacity is limited by the capacity of the converter station at the sending end. In actual operation, it is necessary to allocate the power flow to avoid current limiting overload. Next is avoid power flow tutorial. The third is power flow control scheme. Scheme 1, constant active power control mode. Advantages is it can reduce the frequent adjustment of valves to the transmission power and improve the operation reliability. But according to the wind power prediction, the DC power transmission curve needs to be constantly revised, so it makes the operation management much more complex. And here's the scheme 2, DC power maximum mode based on the constant proportion. Advantage is that it can effectively avoid power flow tutorial, but the disadvantages is that if the power adjustment is too frequent, it may cause the rapid change of the electrical quantity at the fan end, so it may result in the shutdown situation. The scheme 3, DC power minimum mode based on the constant proportion. The advantage is that the loss rate of the system is greater than 1%. So above the 3 scheme, I think the scheme 3 is the best. Next is the system engineering challenges of the program. First, VNC voltage control capability is always insufficient, so system oscillation may cause. Next, the poor damping and low inertia, so faults may develop rapidly. Next, cost needs further reduction. As we can see, the VIC converters and the cables is much more expensive than we expected. And the fourth is hard to meet the demand of fast response in system protection, and actually it increased the potential danger for the system reliability. And the fifth, the optimization of coordination between converter stations is needed. Actually, there are many coordination problems between those stations. And there are also other challenges. For example, the clarification of the protection sequence among core devices is needed, and the ability to distinguish transient faults and permanent faults is needed to be enhanced, and further development of superconductor technology is needed so as to improve the performance of high voltage DC circuit breakers. And the converters are beyond current control, and the active power is determined by external systems. So when an island is operating at full power, surplus power from the failure of external system can extend failure regions. And here's the last part, the summary and lessons learned. First is a summary. This report mainly focuses on the future adaptation of high proportion of clean energy grid collection and long-distance transmission mode. The detailed discussion includes needs analysis, well, from top-level schemes of many countries, and concept development stage, engineering development stage, post-development stage, and challenges. In concept development stage, after analyzing several kinds of system, MMC HVDC transmission system is defined as the optimal scheme. In engineering development stage, networking devices including MMC converters and HVDC cables and protectors are analyzed. And then in post development stage, control and protection strategies and power flow distribution as well comprehensively discussed. And the next part is lessons I learned. Well, after a whole semester, I have learned many aspects about systems engineering. Well, from many aspects, including the definition, the concept specification, and the structure and analysis methods, and so forth. Especially, the principle of trade-off analysis is very impressive to me. Also, by learning the case study, I fully understand those analysis and methods of the systems engineering. Well, that's all. Thank you a lot. Thanks a lot for your help.